Welcome to CE3372 Section 1, Fall of 2020 Water Systems Design. The topic for today is hydraulic network modeling, in particular an introduction to a computer program called EPANET. And you will, by the end of today's lesson, you should perceive that EPANET is a superior way to solve these network simulation problems for engineering design rather than rolling your own code. You probably felt that from last time, but after today you'll actually believe it. So I'm taking the link to the content server, and this lesson introduces the EPANET computer program for pipe network analysis. And the program computes steady state pressures and flows in a network given node elevation, node demands, pipe properties, pump properties, tank properties, and a few other things. The program is mature. The computation engine is well tested, and its main competitor in the computation engine world is something called KY Pipe from the University of Kentucky, but they're quite similar, and they're both well-tested code programs for pressurized pipe network simulation. Most professional software uses some variation of the EPANET engine, usually their own interface, but the actual computations are done identically. A few companies, Innovyze is one I know of in particular, completely reverse engineered the computation engine for some specific speed ups to support their clients, because they were doing a simulation model. Well, they are doing simulation models of entire cities of the size of New York City. So hundreds of thousands of pipes, hundreds of thousands of nodes, demands changing every 15 minutes, pumps coming on and off. And while that was certainly within the realm of the original EPANET, a reverse engineered version could be made to do all that very, very fast. The underlying intellectual technology is the same. And so combining the user interface, either a commercial one or the one we're going to use, which is distributed with the computer program, and the tested computation engine pretty much makes the program fairly straightforward. I claim it's easy enough for a cat to use, which is not true. Their lack of opposable thumb makes it very difficult for them to operate computers. So that's what we're going to discuss today. In the notes section are some readings, the usual water distribution systems. That's sort of our fallback reading in the Land Development Handbook. In David Chin's book, there's about a 20-page section on pipe networks. In Werbs and James, we have pages 130 to 198 are relevant for pipelines and pipe networks. There's a short book by a couple of former graduate students and myself called EPANET by Example version 1. And what it contains is a set of step-by-step examples. So we'll work a few of these in today's lesson, but that's always there in the readings to fall back on. We will probably get as far as, I'm scrolling down to this example and complete it. We won't get to the pump example today, but that's the subject of the next lesson anyway. There's some software links provided. The best way to obtain this software is to go from the EPA distribution, which is this one. It says Windows Installer Official Distribution. The current version is 2.2, not 2.00.12. And you would download the self-extracting program for EPANET 2.2 and run the self-extracting program. Or you could go for 2.00.12, which is what I have on my server. Externally, they don't look much different. 2.2 has some parts corrected, that we're actually not going to explore in this class, but for advanced cases you want 2.2. And there's also the user's manual, the original one from 2000, and there's an online one for version 2.2. And that's the best way to do it, but these are designed for Windows installs. If you are handicapped on a Macintosh, and you have a Macintosh with an operating system that predates Catalina, so Mojave, High Sierra, any of the older operating systems, you can take this link, EPANET Unwind, if it's working, oh it is, and choose this 2.00.12 and download this entire tape archive. It's half a gigabyte, it takes a while. And then you could watch the movie, which shows you how to operate it in QuickTime Viewer, and you would have a functional Macintosh copy. But it doesn't work in the modern Macintosh operating system. So we can blame Apple for that. They chose to change things. In the video links section, there is a YouTube video on how to download and install EPANET on a Windows machine. And I'm clicking on it to be sure that the link is live. And that looks like one of my videos from a while back, and so it goes through the whole install process. The Macintosh hack is shown. This is actually one of the most viewed videos in my playlist. There's quite a bit of comments. It does not work on Catalina or later, so don't even try. And this last one is, I think it's the first two examples. So it goes through the interface in the first two examples, but we'll be doing that today. So if there's no no questions, I will proceed forward. So taking the lesson notes, and I'm going to select lesson 9 PDF. And here's our lesson, EPANET Introduction. So in terms of introducing it, it's designed to make our lives easier as analysts and designers. So the way we can do it is to install it on a PC. And I showed you the video that will go through that. And the video is several years old, but the installation process is unlikely to have changed very much. So from the video, you should be able to figure it out. There's an example of install on a Macintosh. I would advise against that if you're a Macintosh user. If you happen to have VMware in a Windows operating system on your Macintosh, or Parallels in a Windows operating system, to do this, go ahead and activate either of those environments, get into your Windows operating system, and just download and install it as if it's a PC, and it'll work just fine. Then we'll take a little look at the interface of the program and then work some example problems. So the computer program allows us to connect virtual system components and simulate the behavior of a water distribution system in order to decide if the pressures and the demands are met within statutory and customer requirements. Remember, we take water from a source and we transmit it to a treatment facility, and then from the treatment facility, which is really what the EPANET program is designed to do, although you can have a treatment facility within your network, you just simply specify a head loss for that unit. And we could then convey it from the facility out into the network through pumps, put stuff in storage. It goes through appurtenances in order to increase the head loss so that we don't have any zero friction system, and eventually to the distribution line, and finally to the end user. So this little house on a little lot is the end user. Then it goes through the kidneys and the colons of the occupants of the house, and it's the output from that goes into the wastewater system, which is a different part of this class. So the network representation is comprised of the following listed items, and it is a model to simulate the conveyance of potable water at adequate pressures and discharge. And adequate is defined by statute, which was why we were reading the different design guidelines for some different communities. And it all runs around 35 psi at the low end. That's the minimum. And some of them indicate an upper end. Pressure is much greater than 90 pounds per square inch will pretty much destroy residential fittings. They'll work for a while, but not very long. And so we tend to try to keep pressure, at least at the end user, somewhere between 35 and 90 pounds per square inch. Now the large transmission mains, we can certainly design them and specify materials that are capable of operations at greater than 95 psi. But once it's getting out into the neighborhood, that's kind of our target range. So we represent tanks and pumps and pipes and valves and fittings and meters and lions and tigers and bears, oh my, for our network. And the network is normally skeletonized, as is indicated by this diagram that's showing up on the slide. If we look at these areas, there's going to be quite a bit more individual connections that are indicated by this diagram. And so each of these nodes is actually used to approximate the demand at that geographic location of some area around the node. While it is possible that we could build a model all the way down to every customer meter, and in some communities that's done and it makes sense, such a model would be very difficult to maintain, almost impossible to find mistakes in the conceptualization because it would be a big model, big in the sense that there's a lot of parts to it. And so finding conceptualization mistakes would be pretty much impossible from the analyst's point of view. It would they'd be discovered as the model doesn't perform well in certain locations in the community. And so that's not often done. More commonly done is a skeleton model where each of these nodes is used to approximate the behavior of a nearby area. And that's what we're going to do in the subdivision design that you've all been working with, whether you know it or not. The demand estimation that you just turned in, that subdivision, those nodes are going to take demands and distribute them to roughly 6 or 8 houses. And so that was actually part of the purpose of that exercise, is to have those numbers available for when we build a network. So EPANET simulates the flow in the system, and it's for pressurized systems. It's not the right tool for wastewater collection systems. We use something different for that. It's comprised of nodes, or I believe they're called junctions in the program, elements that join two junctions called a link, and links are things like pipes. Pumps is categorized as a link object, and valves are link objects. Links basically go between things, and nodes are endpoints of things. Reservoirs, which is a type of node, which has either a fixed grade, a supplied total head, or a tank where the pool elevation can vary over time. And if that's the case, the time varying behavior is done with something called a demand schedule, and the simulation technique is called extended period simulation. And when that's invoked, what the program is doing is the hydraulics are done at steady flow. So any change in flow rate anywhere in the system the hydraulics is changed instantly as far as the pressure computations are concerned. And that's pretty reasonable even for a real system, because a pressure wave in a pipe that's full is going to propagate at about the speed of sound, which is around 5,000 feet a second for sound in water. So a mile a second. So if your system has 60 miles of pathway, I mean, it would take a minute for a change to be manifest in terms of a pressure wave. And these demand schedules are usually changed hourly, or at least every 15 minutes. So it's a reasonable approximation that when a change occurs, the pressures readjust quite quickly. And then the schedule is used to keep track of what the pool elevation would need to be in a tank as those demands are changing. So either the tank fills or drains. And it's based on the flow and pressure at the beginning and at the end of that change. So at the beginning of an hour and the end of an hour. So it's not a true dynamic simulation, but it's historically has been accepted as a reasonable approximation for design and operation purposes. So to get the program, you've got a couple of choices. You can go to the class website, because I've got some active links that we just demonstrated were working. Or you can Google EPANET and download and install it. You could try Googling EPANET for a Macintosh and see what else is out there. The application bundle that I built, there's a lot of people on the planet. I can't be the only one that bothered to build and distribute an application bundle. Maybe someone else has one that indeed does run on Catalina or Big Sur. And for Linux users, if there's anybody listening right now that uses Linux routinely, the EPANET program, that self-extracting archive, can be coaxed to work using the wine environment. In fact, you're going to see it doing that today. I won't go through the details, but when I demonstrate EPANET, that's actually what I'm going to be doing. I'll be running it on a Linux machine remotely, and it's handling all the graphics interpretation using wine. I've not tested it with a really big model, thousands of pipes, thousands of nodes, but anything reasonably sized for a classroom context seems to work. So getting the documentation, I put an entire slide to this because this is amazing to me. Over several years of teaching hydraulic network modeling, that somehow this step gets forgotten. It's probably a good idea to download the user manual. In the past, I used to say download and print. That was my subtle hint of slapping people in the back of the head. I don't care how you do it, but get the user manual and look at it. User manual is 120 pages. It's not tutorial, and it's laid out kind of goofy. I will grant anybody that. But with the user manual and a persistent search, you can usually find out how to do what you want to do with the program, or find out the equally useful that that particular activity cannot be done. When we build these networks, we're building the topology in a graphical user interface. It's possible to build an EPANET input file, and if I remember, I will export one of them as an input file so we can look at it, and it's just an ASCII text file. You can actually build them from scratch. It uses a card image format, so you would have to read the user manual to see how to build an IMP file. That has utility in certain situations, because once we know the pattern, we could write an independent program that could generate a bunch of different input files and test different conditions for us. But that's certainly not a common activity in typical design or testing a typical design. In that topology, either in the GUI or in an ASCII input file, for each component, that's in the network. If it's a node, the demand is supplied for that node, and the elevation is supplied. That's minimum information for the node, I guess, and a name for the node. And then for link type components, the length and diameter, friction terms. In the case of a pump, we have to independently provide a pump operation curve. It can be very simple. It can be a one-point curve if it has to. And we also provide a connectivity diagram. And so the connectivity diagram was like the node arc instance matrix that we saw last lesson, which had the plus and minus ones and the zeros in it. That's all the information that's required by EPANET. It really doesn't require anything different than the by hand example that we did last time. So here's a list that just says what I just said. Nodes, links, and tanks. All EPANET models, if they're going to run, have to have at least one reservoir or one tank. And generally those would be fixed grade. You would supply a pool elevation. And they behave like the ground does in an electric circuit. If you remember from your circuits class, when you did circuit analysis, you had loops of resistors and stuff. There always had to be a ground to be able to get a unique solution. Without a ground state, we can still solve the system, but we don't have anything to reference pressures to, and so there are infinite number of solutions. And so a computer program by default says, I'm not going to do it, and issues a warning or error message. When we build these things, we usually have to lay the nodes out first, because a link is a connection, and you can't connect something that's not there yet. So the usual approach is to lay out nodes, lay out links, lay out reservoirs. Reservoirs are a type of node, so they can actually be placed during the node layout portion. And then we parameterize or supply the additional input information for each of those elements, and then we're ready to run the simulator. So here's the things that you have to pick. We have to choose what head loss model we want the program to use. Either Darcy-Weisbach, Hazen-Williams, or Chesney-Mannings. You can choose any of the three, but you can't mix it. So you can't have part of the network simulated in Darcy-Weisbach and part in Hazen-Williams, at least in the same simulation. I'm sure there's a way to finesse it, but it's not built in. We also have to select flow units. Cubic feet per second, gallons per minute, cubic meters per second. Selecting the flow unit also selects whether we're an SI or US customary unit system. My advice is do it before actually building a model, because the program does not convert unit system. So if let's say you open the model and you don't have the defaults reset so that you're having download defaults, so it's going to default to gallons per minute. And you build your whole model where pipe lengths are in meters, pipe diameters are in millimeters, and your heads are in meters above a datum. And then you get ready to run it and you realize it's in gallons per minute. At that point, switching the flow units will be just fine because it doesn't have to convert the unit systems into something else. But if you've not done it that way, it could be a disaster. So the usual thing that when I do the professional training is as soon as you open a model, the first thing we do is we select flow units, and then we continue on with the modeling activity. And we'll see that in the example. So as a protocol or a method to do it, here's what I suggest. First, before even trying to open the computer program, sketch the layout on a piece of paper. On that layout, we want to identify pipe diameters, their length, and their roughness values. You probably want to name the pipes. The names can be silly names like pipe 1, pipe 2, pipe 3, just so that you can tell them apart on the picture. Similarly, for the nodes, we want to identify node names, node elevations, and node demands. If there's a supply reservoir or tank, we identify the reservoir and we write the pool elevation. And finally, we identify pumps. And if we have pump curve information, we want to write that down on the picture in problem units. At that point, we're ready to start EPANET and build the model. Because with that layout on a piece of paper, we have something to refer to. Earlier in the class, when we were going through design manuals, there was something very similar that said that an area map is useful for constructing the network, and that's all this particular presentation slide is manifesting. Then once we have it, we can start the program and build the model. So we'll go through these two examples and a third one. I've already preloaded the pictures to where I'm going to use them. And so, well, let's just look at this one, for instance. So this is pipe AJ. So it has a name, and we know its length. And in the problem statement, we also know that it's an 850 millimeter pipe. JC, and then BJ, and so on. So we have names of pipes, and we have names of nodes. In this example, we don't have that, but this is pretty simple. We should be able to get by without any trouble. So let me see if I can go find EPANET in a box. So I'm going to take this tab sheet, EPANET in a box, and I hope it's running right now. Let me get the pass key. And my home network is running a little slow, so there's going to be a lot of lag, which actually will be good for the purposes of a lesson, me talking at you. Then I won't be going too fast. Oh, sweet. I always worry when I do that if it's going to come up red, meaning that the server has shut down and needs some serious maintenance. Okay, so that's normal. It should be giving you this warning that the connection's not secure. The passkey is sent securely, but data is not. So data is in the clear, but really all we're sending in terms of data is pixels. So if it's intercepted by North Korea or Russia or China or whoever our enemy is this week, I'm not too worried. They're not getting anything valuable out of that. They're much more trying to get money from people. So don't send monetary information. You don't need me to tell you that. So this is the desktop that we would expect to get. And I've pre-placed those examples in Hydro 1 examples. And for example 1, oh, that's interesting. Here's a bitmap, and I'm going to open it with Chrome because I know Chrome can read bitmap images. And there is our picture. So we're going to actually make use of that in the EPANET program. There's some files here already. There's a report file, and there's this morning's live network and this morning's live report. And then I left one called solution. But we'll start from scratch. So this is going to call example 1, I guess, evening. So I can close that. That's where I'll store the files, but I'll operate them through the EPANET. And so now I'm going to start the EPANET computer program. So I've double-clicked on that launcher script. If you've downloaded your own copy of EPANET to your Windows machine, some of what I'm doing has no relevance in Windows, and so just ignore that until I move to the next thing that makes sense. So here's the EPANET graphical user interface. I'm going to attempt to resize it on my computer so that it fits entirely in the presentation window. Oh, it's actually performing today. Usually it doesn't do that with an audience. Okay, so that's about my network lag right now. And I'm resizing everything so it'll all fit in the window so that I can give you a tour of the interface. So this guy, the browser, pretty poor name for what it is, but it's all the real work happens in here. It's real important that you don't lose it. By losing it, I mean it finds its way out of the window. There is a way to restore it, but I forget which of the menu items does it. So I've always found it smart to just not lose it. You can put that over there. Now I'll resize this. And okay, we're pretty good there. Now let's handle the vertical resizing. And on your home machines, if you install it in Windows, you shouldn't have to do this shenanigans with resizing things. Okay, so that's all fitting in the interface window. So this is the interface, and let's see what we have here. Up at the top, it's telling us this is EPANET 2.2. There is menu items, file, edit, view, project, report, window, help. And the help topics is actually working on this particular machine, which is, I found that somewhat unusual. Down on the bottom, we have a box here that's telling us the flow unit. So currently it's set to gallons per minute. And we have a picture of a faucet with black. And so if it's a black faucet, that means the simulation has not been run yet. Forget what the 100% means, and this XY is keeping track of where the pointer is on the drawing canvas. You notice when I exit the network map drawing canvas, X and Y stop changing. As soon as I enter it, they take on values. So it's possible to turn some features on and, in some context, georeference information. So the first thing we're going to do is go to the project window, and I'm going to set defaults. Go into hydraulics, and our first problem, I'm going to put it into cubic feet per second, because we've done that exact problem earlier in the class on the online calculator, and I believe the answer is somewhere around 11 or 12 cubic feet per second for that problem. And let's switch to Darcy-Weisbach for our head loss formula. In properties, we can put things here, and we're going to want to change the pipe roughness default property, but let's go get a value first. So I'll press the okie dokie, and now the flow has changed to cubic feet per second. So I'm in the flow units that I want to use. Let's go to help, and let's see what happens when I choose units. Oh, that was a mistake, actually. Oh, but I get the whole help menu. Index, and I want roughness. There's a table in here that has roughness values, so we'll just take advantage of that. Except I'm not finding it because I'm not searching it correctly. Roughness coefficients, there it is, don't go away. So it has a little teeny table of roughness coefficients, and for cast iron, 0.85 and so forth. And it's in weird units, but these are the actual numbers that you can enter into the program. So I'm going to copy that 0.85 because this first problem is a cast iron pipe that's joining the two reservoirs together. It's probably a dumb materials choice, but that's the problem. So I've copied that 0.85. I will exit the help deal. I'll go back to my defaults. And in properties, I will oh, that's right. This doesn't have cut and paste in the usual fashion. Okay, so our properties are now default. Alternatively, as we build the elements, we could just override where the default properties is needed. So let's now get a picture of our backdrop, which is useful for drawing the network, and which is why I tell, why I mentioned in the protocol to draw everything on a piece of paper first, because you can take a photograph of that paper, convert it to a bitmap file. I think you can also read JPEGs, but it screws it up. So you make it a BIM and open it, and there's our picture. So what that does is it helps us draw our network. So we're going to make one more change. We go to the View menu, Options, and I'm going to make things big enough to be able to see them. So we'll make our nodes a size 9. Make our links, we'll leave them at, we'll make them 2. Flow arrows will be fancy. We'll make them big. Okie dokie. So that'll come in handy later on. Start with nodes. So we'll put a junction there, a junction there. We'll add reservoirs, which are a type of node. We'll put one here, and we connect everything with pipes. So I'm going to connect this reservoir to this node. When I specify that pipe's diameter and length, I'm going to make it very short and a big diameter, so there'll be no head loss between the reservoir and that node. Now we have to do it this way rather than just connect the two reservoirs, because EPANET by design has to have at least one junction node in every simulation that's going to work. So we have to use our hydraulic knowledge in order to produce the kind of system that we want. So putting these short, large diameter pipes in, essentially we're producing zero head loss connections to the nodes from each of the reservoir. So it's as if that node is actually in the reservoir. Would be a good mental model. And now we will connect the two pipes with a cast iron pipe. And we go back and we're going to now have to supply information. So what's currently reservoir 4 in our model, we need to give a total head value to it. And I'm thinking reservoir 4 is at 10 feet elevation above some reference. Go to reservoir 3, and if reservoir 4's pool elevation is 10 feet, then reservoir 3's pool elevation is 30 feet, which produces the 20-foot difference. And let's give the reservoir a meaningful name. So I'll call it Upper Lake, which is every bit as dumb as reservoir 3, but at least it's a name. And we'll call the lower one Tailwater. which is also simply a name. Every bit as dumb as Reservoir 4, but still a name. So now we've named those elements. This pipe, let's make it short, 10 feet long and 36 inch diameter. Notice the roughness coefficient's automatically placed for us. And we'll just call this short pipe 1. Not very ingenious of a name. And this one we'll call short pipe 2. Also, we'll make it pretty short and a big diameter. So there'll be no head loss from the reservoir to the node through either of those pipes due to a localized node. And then the remaining pipe is pipe number 3. And its diameter is 24 inches based on the drawing. And it's 2 miles long, which is 10,560 feet. So the last things we have to do is decide what the elevation of each of these nodes is. So the elevation of the node defaults at 0, but that would mean that that node is 30 feet below the pool of that reservoir, which, well, that's quite possible. It seems kind of dumb. So I'm going to put the elevation at 20. So there's 10 feet of water above the node. And I want to have the same property here at this node. And so if we leave it at 0, there'll be 10 feet of water above the node. All right, we can check our connectivity by turning off the backdrop. And that indeed looks like what we want it to look like. On the map, we can, for the nodes, we can do, let's do pressure. And for the links, we will do flow. So what we're doing is we've now created these color schemes that when we run the simulation, the objects will change color based on the color scheme. I don't find that extremely useful, but we'll play another trick in view options, where go to the notation, and I want to display the node values, display the link values, and temporarily I'll put the IDs in. And we'll leave them at the default font size. No, we'll make them bigger. It should be good enough. And so you see it's just that short pipe 1, the upper lake, node number 1, pipe number 3, tailwater, short pipe 2, and the hashtag NA means that those values aren't computed yet for each of those objects. I'm going to turn off the IDs because I think they're going to get in the way of this particular problem. So we'll go back to options, and we'll turn off the IDs. Choose the okie dokie. And so for any node element, the program is going to report its pressure. That's what we've told it over here in the map tab. And for any link element, it's going to report the flow rate, and it's going to report it in cubic feet per second. If it's a positive number, that means that our connection diagram, so let's look at pipe 3. Pipe 3 currently starts at node 1 and ends at node 2. Node 1 is this guy right here. If it's positive based on the connection diagram, we'll get a positive number. If the flow is the opposite direction, we'll get a negative number. And there's a reversal tool so that if you're doing this for a client who can't fathom negative numbers, you can reverse it. The arrows are always correct, and then the numbers are adjusted by the reversal. I'm moving these reservoirs a little bit away from the nodes so that when it computes values, we'll be able to see them. So it's tempting to try to get the drawing perfect, but there's absolutely no benefit unless you're doing a presentation to a client. Because moving stuff around in the drawing has no impact on the actual calculations. Go ahead and I'll put my backdrop back in just for fun. And there's our model. And now we want to go ahead and run it. So to run it, we can either choose the lightning bolt, which is called run, or in project, run analysis does the same thing as the lightning bolt. So I press the lightning bolt and we wait and we get the most wonderful output from a computer program that you could ever hope for, which was the run was successful. What that means is that whatever input we gave it, it was able to make calculations and produce results without generating any warning or error messages. Doesn't mean it's right yet. We still have the obligation as designers to check the results and see if they make some kind of sense. Other things that come out of here is you get warning pressures are negative somewhere in the system, or you get error and then a cryptic error message that sometimes they're a little hard to decipher. But we got success, so we're happy with that. Press OK. And now it's told us that the flow rate through the 2-mile pipe is 11.89 cubic feet per second. The pressure at both the upstream and downstream node, each of which are 10 feet below the water surface, both 4.33. So in this particular setup, the flow is entirely gravity flow. That's kind of interesting. You'll notice the pressure in each of the reservoirs is reported as 0. So the reason that is the way the program computes pressure is pressure is equal to total head minus the elevation of the object. Well, the total head at a reservoir and its elevation by default are usually the same thing. But if we switch from pressure to head, we now get more interesting information. So the heads at each of those places, the head at the upstream reservoir is indeed the pool elevation of 30 feet, which is what we supplied. The head at the downstream reservoir is indeed the pool elevation of 10 feet, which is what we supplied. The total head at the downstream node is also 10 feet, and so you can see there's no head loss in that one link, the short fat pipe. And at the upstream end, the same behavior is observed. We have 30 feet of head pool elevation for the reservoir and 30 feet of head at the first node. Again, no head loss between the reservoir and the first node. But from the upstream node to the downstream node, there's the 20 feet of head differential, which is what we expected. You can actually select individual objects and interrogate the database that was generated for them. And computed values are normally shown in this kind of yellowish background. So the flow is 11.89 cubic feet per second. The velocity is 3.8 feet per second. The head loss is 1.89 feet per 1,000 feet of unit. Computed friction factor by Darcy-Weisbach is 0.017. Those numbers all are plausible. I check the friction factors a lot so they don't get ridiculously small or ridiculously big. The program will report a friction factor regardless of the head loss model that you use. The friction factor is computed as if it was a Darcy-Weisbach friction factor, but it will use the head loss model you tell it to. You can use the results of this to convince yourself that your layout makes sense. Friction factors shouldn't go outside the range of values that are tabulated or on the Moody chart. So to save the output, we can go Save As, and it will go back to the last directory I was in, which happened to be the correct one. And I'm going to just modify that. So it's the evening one. And that file we just saved is a binary file. If instead we want to export the network, we can export it to something called an input file, .imp, choose Save. And we've saved the input in an ASCII format. We'll go take a look at that shortly. We can also generate something called a full report, and it's going to save a report to file name, example1 live evening RPT. That's also an ASCII file. We'll take a look at it shortly. So we just saved our work. The only thing that we don't really get to save is the pictures. And now I'm going to exit the program. So exit is really easy. You click on the exit doodle, or you can actually click on the X here, and that looks like a clean exit. So let's go look at those files we just created, just so that you're aware of what's there. In the Hydro one is in example one. Well, first we'll look at the report. So I'm going to open it with Mousepad, which is like Notepad, which should be a little lighter weight. I mean, it should load faster. And here's the output report. It told us when we did the simulation. So we did it at 6:24 p.m. server time. So the server is not in the same time zone we are. It returns the name of the input file. It gives us the link node table. So this table is actually pretty useful. It tells us that the link named short pipe 1 starts at Upper Lake, ends at node 1. The link named short pipe 2 starts at node 2 and ends at tailwater. And the link named 3, not very ingenious name there, starts at node 1 and ends at node 2. It tells us the length of each link, and it tells us the diameter. It also gives us node results in this panel. So we have 4 nodes, node number 1, node number 2, Upper Lake, and tailwater. It tells us the demand at each node. In this case, Upper Lake flow is leaving the node, so it has a computed negative demand of 11.89. Tailwater flow comes into the node. It has a computed positive demand of 11.89. It reports the total head at each of the node, and it reports the pressure at each of the node. It's also reporting water quality, which we didn't even activate. Nodes that are fixed grade nodes, it's identified by the word reservoir. And I believe if it's a tank, it will report it as a tank. We can add a column when we define the report if we wanted the node elevations. It doesn't default that. And then the last part are the results for the link. So we have the 3 links, short pipe 1, short pipe 2, and link number 3, and then the invisible one's the missing link. And the flow in each of them is 11.89 because we had no external demands in this system. And it tells us the velocity in each link and the head loss per 1,000 feet in the link. And then the status, open or closed. In more elaborate systems, it's possible to close links during a simulation to see how the system behaves if that link was not there. So that is the output report, and that's an ASCII file. So you can open it with any text editor. if you do it on your Windows machine and you just double click on the file, it's going to ask you what you want to open it with. Because even though it's an ASCII file, none of our computers are well behaved enough to know that. So this next one, the .NET file, is a binary file, and they won't even let me try to open it with a text editor. We could open it with a hex editor, but I don't want to go there. It's really not that interesting. It's just a byte stream of bytes in hexadecimal. That's all we would see in the hex editor. This last file I want to look at is the .inp file. And so this is all EPANET really needs, is the INP file. We don't need the graphical interface, and here's what an input file looks like. The nice thing about this is this file, because it's just an ordinary ASCII file, you can email it to someone, they can make changes and run it, or run it as is, and they don't need the background picture. So it has a title section, junctions, reservoirs, tanks. So all these sections in the square brackets identify the different components of an EPANET model. The blank line ones, of course, are obviously not used. And then at the later part, we are instructing the simulator how to work. So this is equivalent to when we brought up that default window and we changed the model type, Darcy-Weisbach, that's contained in the options category. So if you end up using the program a lot, which won't be in this class, but if you leave here and work for a place that does a lot of hydraulic simulation, design, and modeling, you'll get to a point where you will tend to go straight to the input file because you know how to interpret it. But that comes with quite a bit of practice. And if you don't have to use this a lot, I would say that the point of the graphical user interface is so that you can use it without maintaining the high level of knowledge of what an input file is supposed to look like. So that was example one. Not a very difficult example. It probably actually took us longer to do it in the software than it would have been done to do it by hand. But we accomplished two things doing it in the software. First, we proved that we get the same answer. And secondly, we convinced ourselves that we can use the software to build meaningful models. So now we're going to go look at the second example, which is the 3 reservoir problem. So this one will be approached the same way. The graphic is already loaded. The thing I'm trying to remember is the pipe diameters will be 850 millimeters. We're going to want to do this problem in SI units. The flow unit that's most convenient to use is going to be liters per second. It doesn't have cubic meters per second, but it has liters per second, and they differ from each other by a factor of 1,000. The water elevations are known. The pipe lengths are known. This junction, its elevation is unknown, but we can pick a number for it, or we can leave it at 0. It won't hurt anything. All the pipes are ductile iron. We'll use the cast iron value that we already have coded into the program. So returning to our EPANET world, we'll go and launch the program again. And we didn't have to close it and launch it, but I'm doing that to be consistent. So we'll go to the project, defaults. Again, we're going to want to do Darcy-Weisbach. And we'll want to set the roughness to 0.85. And if you recall, all these pipes were 850 millimeters. So out of laziness, because I don't want to change these 3 times, I'll just go ahead and put it in default, hit OK, and we're now ready. We'll go to the View menu item, choose Backdrop, Load, and now we have to find the file. It's contained in example 2. It's been pre-placed. And there you have it. And so now we will start to build the file, build the model. So we have the drawing, things are labeled. What are the first objects that we have to put in to be able to create this? So that's an interactive question. You can type it into the chat box or unmute yourself and state what the objects are.
Your nodes and reservoirs.
Excellent, that's correct. We will put in the reservoirs and nodes. We're actually going to label them, so it doesn't matter which we do first. I'm going to start with reservoirs. So I'll put reservoir A, B, and C. Oh, I really need to get the Jackson 5 and play that in the background when I'm doing this, because ABC is easy as 1, 2, 3. And
for this one, did you want to change it from gallons per minute to cubic feet per second, or we leave it?
I want to do it in liters per second. So thank you for bringing that up. I'll take care of that right now. So we go into Project, Defaults, Hydraulics, Flow Units. Liters per second is the most convenient one. The reason I do that is I can convert liters per second to cubic meters per second almost by just looking at it. I actually don't understand why they don't have cubic meters per second, although it's actually a big unit, and in real world that's not going to be that common. So we've got the nodes drawn. Currently they're kind of small, so we'll go to the View menu and we'll make them bigger. This will be easier for us to see. So, okay, those are big nodes. I can see those. Our next thing is to draw the pipes. And then we'll go back and we will parameterize the nodes. So I'm going to start with pipe AJ. Now, I could click here on the node and then strike all the way to J, and it's going to draw a straight line. And that's fine. But sometimes for clients, they can't handle straight lines. And so I got this pencil and I can follow a curve. All I'm doing is slowly moving along the curve and clicking on it. Again, the graphics, unless we turn on certain features, is simply to help us see what we're doing. It has no specific meaning spatially or in terms of computing lengths. This is a hard curve to follow. And believe it or not, there's our 3 pipes. And now we'll go ahead and go back to the selection cursor and we'll start working on our objects. So Reservoir 1, I want to rename it to Reservoir A. Its elevation is 100. And that's about all I need on that. See if this will work. And usually I can just click to the next item and the dialog box will move along with me. Indeed it does. Okay, so now we'll go to Reservoir B. We'll put its total elevation of 80 meters. And that's it. And now we'll go to Reservoir C. put its total elevation at 60 meters. And we're good to go there. And now we can go to our junction, and we either have to specify an elevation or not. I'm going to put the junction at 70 meters, just for the heck of it, because we don't know what the junction height is in this particular problem. So now we've set all the information we can, and we want to call this junction by its correct name, J for junction. Now we'll go to pipe 1, and we will give it its name. This is pipe AJ. We can tell by start and end right there. The pipe is 900 meters long. It's already got the correct diameter and already has the correct roughness. Now we'll go to pipe BJ. Specify its length, which is 800 meters, and it already has the correct diameter and the correct roughness. Now we'll go to pipe CJ, and we'll specify its length, which is 700 meters, and it too already has the correct diameter and roughness. And we are ready to do some calculating. You notice down here, this yellow area, we have the pound NA because we haven't made any calculations yet. Those are all calculated values. So that's the convention that the program uses to identify input versus a calculated value. So I can close the dialog box. I can close the backdrop, verify that the connectivity looks right, looks good to me. I'll put the backdrop back on. And let's be sure we're going to get arrows when we run it. So I want flow arrows. We'll do filled ones, just to be different. I like to make them big. And notation. Let's report node values and link values. Link values. And hit OK. All right, we're good to go. And so now we can attempt to run the simulation. We'll choose the run clicker doodle there. And the run was successful. Yay! And we can look at pipe AJ directly, or we can go to the map tab, and we can tell it to show us the flow. So pipe AJ has 2.474 cubic meters per second, or 2,474 liters per second. Pipe BJ has 295 liters per second, or 0.295 cubic meters per second. And pipe JC has 2,769 liters per second, or 2.77 cubic meters per second going through it. And it shouldn't be too hard to convince ourselves that that number plus that number equals that number, and they have to. In the case of the nodes, we can, let's plot the head first. So the head of each node, I can barely see it. I'll change the background. And black will work. And that helps. So the head at Reservoir A is 100 meters, Reservoir B 80, Reservoir C 60, and the head at the node is a 79.7 meters. So there's very little head difference between the 80-meter reservoir and the node, and there's not that much flow comparatively to the other pipes. If we switch from head to pressure, what we'll see is that at the reservoirs, the reported pressure will be 0 because the total head and the reservoir pool elevation are the same. And the head at the pressure at this node is 9.73 meters. 10 meters, it's close to 10 meters, which is about 1 atmosphere. So it would be 100 kilopascals or so. When we're in the SI units, the pressures it reports are in meters of water. And so an analyst has to know how to convert with that. It's a shame it doesn't report it in kilopascals or something meaningful, but that's okay. It still did the hydraulic calculations for us. So there's the example there. So let me go ahead and save it. And we're in the right directory, but we'll go ahead and call it so we've saved the network file or the binary file, so that saves everything except the picture. And we could, if we want to, export the network, which produces an INP file. And I will close off this example, and let's see how much for time. 6:30, 7:30. About 5 minutes. That's kind of pushing things, but we'll see what we can do. Let's look at the third example. And rather than go back to the content server, I'll just go straight to building the third example. I'll have to go back to the... No, actually, I think I have all the information I need in the picture. We'll see in a second. So the third example, and this is, again is taken from EPANET by example, the document that my graduate students wrote a few years ago. It has all the information we need except for the node elevation. Okay, so here is our network drawn out on a piece of paper. Everything of importance is labeled, and so we're ready to begin. So as before, the first thing we do is we put in reservoirs and nodes. So I'll go ahead and put that reservoir in, that reservoir in. I'll put in nodes A, B, C, D, and we will now connect everything with pipes. So there'll be that pipe there, that pipe there, and I drew the two reservoir to network connections first, just out of habit. And well, now we're ready to go supply parameters to things. So first, let's do pipe AB because we have the information right there in the picture. Its length is 700 meters, 250 millimeter diameter, and let's stick with the cast iron, 0.85 roughness. Go to pipe BC. Its length is 800, diameter 300, roughness 0.85. Pipe CD, 1,200, diameter 350, roughness 0.85. And pipe AD or DA is 1,400 millimeters in diameter, 0.85. The next thing I'll do is I'll parameterize the two nodes, node B and D, and then I will actually take care of the pipes that connect the reservoirs. We'll put the head in the reservoirs, and then we got to remember to change flow units because right now it's expecting gallons per minute. So right now the computer program thinks that these are U.S. customary values, and they don't make sense. A 4,000 foot diameter, 4,000 inch diameter pipe makes no sense. And so now we're ready to go to the nodes. So we'll go to node number D, and we'll leave the base elevation alone, but now we have a demand, and we're going to do this in liters per second. So 0.2 cubic meters per second is going to be 200 liters per second demand leaving the network. And at this end, we're going to have 200 liters per second entering the network. And you'll notice I slipped in a minus sign right there to get the demand to be injecting into the network. Okay, so a few things left. Take care of this reservoir. We'll set its total head, 75 meters. This reservoir, total head, 70 meters. This pipe, we just want it to be a small pipe, a short pipe, and a big diameter. We'll make it 1,000, and we'll again stick with the same material. Do the same up here. We're almost ready to run the simulation. Actually, I'll make it a full meter in diameter. That's a big pipe. Even I can crawl through that. I believe we have everything set, and all we have to do is change our flow units. We can do that in project defaults, hydraulics, flow units to liters per second. And we probably should use the correct head loss formula, because if we leave Hazen-Williams head loss formula, we'll get an error. And I'll go back and demonstrate that in a second, but we'll do it correctly the first pass. Hit OK, and now we should be ready to do simulation. That took 6 minutes to build that model. Now, admittedly, I've done this a lot, so we can take a quick check by turning off the backdrop. Looks right. Turn the backdrop back on. We will prepare the output view. Big flow arrows, notation. We just want values. And we're set up to do pressure and flow right now. So actually I'm going to go with head. Head and flow. So now we're ready to run the simulation. We run it. Run was successful. And we now have, I wish I could get it to quit being yellow. You can't see yellow because of the background. But we now have the flow rates in liters per second in individual pipes. We also actually have the flow directions. So coming from node B, water leaves node B through these two pipes, and the sum of these two values should be the 200 liters per second. At node A, there's additional makeup water coming from the nearby reservoir, and then that water moves down to node B, D, and exits the system. Moving down from node B, a portion of it is extracted to this reservoir. Another portion continues on down to node D. So we have solved our network for this particular example. So that concludes the presentation for today. Let me go ahead and save this example. Example 3. And that would be all one would need to recreate it. And I will now exit the program. If by any chance you choose to use the this web served desktop, that's fine. That's what it's for. It's intended for you all to use. Be sure before you leave it that you clear off the desktop and close everything, and then exit by going to this icon here, which is the disconnect icon. Disconnect from the desktop and wait till you get back to this screen, and then go ahead and close it. That will preserve the state for the next user. We will pick up again on Thursday when we look at pumps and a little bit more on EPANET, and then we'll create an exercise where we'll use it. So your homework will be we're actually going to use that subdivision that you've already been preparing data for. So that will be the EPANET model that we do as homework. So with that, I want to wish you all a good evening, and thank you very much for your attention and patience, and thank you for participating when I asked you to unmute yourself, and I will see you next time. So goodbye, everyone.